All right, now we're going to see how all this business about integration and finding antiderivative relates back to motion in a straight line. And when we talk about motion in a straight line, there's kind of three important functions that we deal with. There's our position function, which we generally call s of t, and this describes the location of the object at time t. We have our velocity function, which we normally call v of t, and this describes the speed and the direction of the object at time t. And then we also have the acceleration function, a of t, and this describes whether the function is speeding up, slowing down, or changing direction at a certain time t. And as we've seen, these functions are kind of related to each other. So far we've looked at how they're related by derivatives. So the velocity function is just the derivative of our position function. And the acceleration is the derivative of our velocity function, or it's the second derivative of our position function. So when we think of these functions, we have our position function, we have our velocity function, and we have our acceleration function. And what we've seen so far with derivatives is if we differentiate the position function, we get our velocity. And if we differentiate our velocity function, we get the acceleration function. So if we do our second derivative here from our position function, we get the acceleration. So that's what these relationships say. Those are how everything's related by derivatives. But now that we're starting to see antiderivatives and integration, we can work backwards. And so there's a corresponding relationship in terms of integrals. So for instance, if we were to integrate our velocity function, well, that would give us back our original position function, but with a little ambiguity. That business of plus c, we'd have to figure out what that constant is to know the position function exactly. And that's what we're seeing here. If we work backwards from velocity, if we integrate, we'll get back our position function almost. And then we can do the same thing for acceleration. So if we integrate our acceleration function, we're going to get back our velocity function plus, usual thing, plus some constant, unknown constant c. And that's what we're seeing here. If we work backwards from acceleration by integration, we get our velocity function. And so this is the kind of the way to keep it in mind. So if we know our position function, we can find velocity and acceleration by just differentiating however much we need to. And if we know acceleration, we can find velocity or position by integrating as much we need to. And then if we know velocity, we can go from there if we want position or acceleration. So these are really the ideas to keep in mind. We can move back and forth between these three different functions as much as we need to by using derivatives or integration. And so when we talk about objects moving in a straight line, we do normally think of units. And so when we differentiate, each time we differentiate, if our functions here, these are functions of time, each time we differentiate, we've seen this before, what we would do is we would essentially divide by another unit of t, since we're differentiating with respect to t. So if we're differentiating with respect to t, when we talk about units, we're dividing by another unit of time. So position, say it's measured in meters. When we look at velocity, it's going to be measured in, say, meters per second. So we've divided by a unit of time. And if we were to differentiate again, well, what would be the units for acceleration in that case? Be meters per second, or meters per second squared. Now, what integration does is instead of dividing by a unit of time, since we're integrating with respect to t, what integration does, so if we were to integrate with respect to time, what this is going to do to our units is it's going to take whatever units we have and it's going to multiply by units of time. So when we integrate with respect to t, that's like multiplying in another unit of time. So if we're starting with meters per second and we integrate once, well, we're going to multiply in a unit of time. So we'll go from meters per second to just meters per second. And if we're at velocity and we integrate, the units are going to be, we're going to multiply in another unit of time. So it'll be meters per second times seconds. So it'll be back to meters. So when we differentiate, we kind of divide by another unit of time. And when we integrate, we kind of multiply by a unit of time. All right, let's try an example. So initially, the top of a rocket is 8 meters above the launch pad. And we know the velocity function for this rocket t seconds after liftoff. And this velocity function is given by v of t is equal to 6t plus 0.5, and the units here are meters per second. So what we want to do in this example is we want to find the height of the rocket at time t. And for our purposes here, we're going to assume that this rocket is fired vertically into the air, so its motion in a straight line. And what we're doing here is the height or position of our rocket is the distance measured from the top of the rocket down to the launch pad. So maybe a little picture might be helpful. We have our little spaceship here, ready to blast off. And then we have our launch pad. Here we go. And what we're doing is the height is being measured from the top of the rocket down to the launch pad. And when this thing blasts off, it's going to be motion in a straight line. So it's just, think of it as just going straight up into the air. All right. So that's a little picture, kind of help think about how this thing's going to look. All right, so what we want to find, we're given the velocity function, and what we want to find is the height. We want to find the position of our rocket at time t. And so if we go back, we know our velocity. We want to find the position. So that means we got to integrate. So we want to find, step 1, integrate. So velocity, or position, really that's the function that we're after here. Our position function is just the integral of our velocity function. All right, so let's fill in our velocity function here. We're going to do the antiderivative of 6t plus 0.5. We can go term by term and just integrate each of those. So when we do that, we get 3t squared plus 0.5 times t, and then plus c at the end, our constant. Now, this is kind of the most general antiderivative. So there's this kind of vagueness. There's this arbitrary constant here. And we need to find this. So that's the next step. We're going to find plus c. And we do that using, as we've seen, we need to use an initial condition. And so we need to go back to our problem. What is the initial condition? Well, we see this kind of wording here that the top of our rocket initially is 8 meters above the launch pad. So what this is saying is that at time 0, so starting initial condition at time 0, and what we're doing is we're thinking at time 0, that's when blast off occurs, and it starts moving up. So 0 is when this rocket is launched. And so S of 0 is going to be, well, what is the starting height of our rocket? And this is 8 meters. So starting, our initial condition here is S of 0 is equal to 8. So that's what our initial condition is saying, but what do we actually have? So this is what we want it to be. What do we actually have? So this is where we look at what we've calculated so far for our positions function. So we know S of t is equal to 3t squared plus 0.5t plus c. And let's plug 0 into that and see what we get. So I'm going to, why 0? Well, that's the time we have for our initial condition. So I'm going to plug 0 in here, I get 0. Plug 0 into here, I get 0. And then I have my constant c. So when we plug 0 in, just be careful. You don't always just end up with the constant. This one we do because we're plugging into a polynomial. But if the function is something different, you actually have to plug 0 in. You just don't actually get c necessarily. So it's easy, kind of an easy little mistake to make. You have to plug whatever time value is given for your initial condition. You have to plug that time into the function. Sometimes you're going to have something other than just c. But here we get c. All right, so we need to reconcile these now. So we want these to be the same. So we set them equal to each other and we solve for c. And when we do this, we get 8 is equal to c. So set these two values equal, and that pretty much does it. Alrighty. So we've set our two values equal to each other, and now we update our function. So now we answer. So S of t is 3t squared plus 0.5t plus 8. And instead of writing c, we've actually filled in what that c value is. And then our units here, let's pay attention. So for velocity, our units were meters per second. And since we've integrated once, what we're going to do, we've integrated with respect to time, what we're going to do is we're going to multiply this by our unit of time. So for our position function, the units are going to be meters. So m over s times a unit of time gives us just meters m. All right. So that's really the game we can play. If we're given one of these functions, we can work backwards or forwards however much we need to figure out the other functions. And the only thing to keep in mind is if we're working backwards using some integration, well, that might take a little bit more knowledge of the system. We need to have a little bit extra information. All right, so we'll try another example, but this is basically the game to play.